For chapter 14, we're going to look at 5 kinetics problems. We're going to start with this problem where we're looking for a rate of change. Specifically, in this case, we want to know what the rate of change for hydrogen gas is at 45 seconds if the rate for hydrogen chloride gas is a given rate, in this case 0.030 molar per second. So we're already given the rate of change, so we can use the balanced chemical formula to be able to find out how these two relate to each other. If, on the other hand, you'd simply been told something like you generated 1 molar of hydrogen chloride gas in 60 seconds, you would first have to find the rate for that one by dividing the molarity change over the amount of time passed. But for this one, we're not going to have to worry about that. So let's get our equality. So first we know the gas that we're making, the one we already know about, is HCl gas. For that one, we have 1/2 delta HCl over delta T. So our hydrogen chloride gas over time, the change of that is going to be related to our change in hydrogen gas. Remember, this 1/2 here is here because there's a 2 up here, and this side is positive because it's a product, so we're making it when we're looking at the rate. On the other hand, for our hydrogen gas, it's going to be negative because it's a reactant. It's going away. And then I'm going to write this. You don't have to, but I'm going to write 1/1. There's a 1 coefficient in front of this, so it's like there's nothing there, but that's where it comes from. That's where that part of the equation is. It just doesn't get written usually because 1/1 is 1. So I'm going to put a delta here, H2, over our delta time. So now we need to substitute in what we know and solve for this. So now, when I get this, let's see, I'm going to get that we have 1/2 of our change in HCl, or our change in HCl we know. So I'm going to plug that in. Let's get my eraser. So now, there we go, back to our pen. So we have 1/2, and we know this one. This one is equal to 0.030 molar per second. And it's going to be equal to negative of the one we want to find out about. Okay? So when we plug this in, we'll multiply 1/2 times this, and we're going to get 0.015 molar per second is equal to the negative of the rate of change for hydrogen gas. And so then we'll move the negative over, and our answer will be negative 0.015 molar per second. This is our rate of change for the hydrogen gas, which is what the problem asked us to. Make sure when you're doing these that you pay attention to what the problem specifically asks, as it might be asking for a different component than this. But we found the one we were looking for. That means we're going to lose 0.015 molar of our gas every second when we're at 45 seconds. Remember that our rate of change changes with time for many reactions, so it'll depend on the concentration we're at, but this is the rate of change right at over our 45-second period. This is the average rate of change we have. So now, let's look at rate order, which really is one of the primary things we're doing in this chapter. So we're going to do 2 practice problems with rate order. So we'll do this one first. So here we're asked for what is the rate law. We're specifically told to determine the value for K in addition to determining the order. So we're not asked for just the general rate law where we don't have to worry about solving for K sometimes. Here we're asked to solve for K in addition to finding all the orders. So first, I'm going to try to, I need to find the orders for A, B, and C. So when I do this, I'm going to start by looking for A. So if we look at our trials, I see that between trials 1 and 2, B and C don't change, but A does. That's going to make these a good trial to choose. So I choose trials 1 and 2 to help me compare these. And then I can tell I triple my concentration of A. I also triple my rate. Since they are both changing in the same way, A is going to be first order. We can then check for B, and B is best done by comparing trials 2 and 3. See here, A doesn't change, C doesn't change, but B doubles. When B doubles, the rate quadruples. That means that the rate is changing at the square of the concentration. Remember, if this had tripled and this was second order, this would non-tuple. It would multiply by 9. So it's not just that we multiply by 2 again or something like that. It's only in this case because 2 squared is 4. So B doubled makes rate quadruple. That means that B is going to be second order. Remember, first or second order is not about the coefficients in front of A, B, and C. Those coefficients don't matter for your kinetics in terms of determining order. They can in your elementary steps, but when we're looking at something like the overall reaction, we're not worried about how many are there. We then have to determine C. Trial 3 and 4, we notice that C doubles, B and A stay the same, and the rate stays the same. that means that C is going to be 0th order, or 0 order. That. So we don't have to, so it is not changing. Come on, keyboard, stop it. We'll move you somewhere there. Having to rearrange a few things real quick, because my keyboard has decided it wants to fall on top of my workspace. Okay, so we've got our orders, or A, B, and C, so this is the first half of our problem. So now we have to actually find our K. So I'm going to do this by writing my rate law, which is rate equals K, which we don't know yet, A, and B squared. Remember, I don't have to write a 1 here because first is just something to the first power is what we assume normally. And C was to the 0 power, so it's not even going to show up in the rate order. We're then going to need to solve for K. So I'm going to rearrange this equation so that K is equal to rate divided by A times B squared. Notice I just divided both sides by A over B squared, and then I just wrote the K on the left because I like having my variable on the left side. It's fine if you kept K on the right and put all this stuff over there. So now I need to actually plug numbers in and solve for K. So I'm going to use trial 1 here. It doesn't matter which that you use. So I'm using this stuff and this. We don't need C since C's not in the equation. So I'm going to have 0.0050 molar per second divided by, we're going to have 0.100 molar, and then we'll have 0.100 molar squared. We plug all that into our calculator. We're going to get 5.0 times, or just 5.0, no times. And I'm putting the zeros, you could do 2 sig figs because of our rate. I would also be fine if you did 3 sig figs because we've got squares and stuff, so I'm not as worried about it as normal. So we have 5.0, and then I'm going to have molar to the -2, seconds to the -1. That's because we keep this per second because there are no seconds over here other than it. And then I have molar divided by molar cubed, so I end up with a molar squared on the bottom. Remember that this unit here, I'm going to circle this thing, is the same thing as writing 1 over molar squared second. Same idea. So that's what we're looking for, and that'll get us through our rate order. This is how we do it by visual inspection. I also want to remind you that it doesn't have to go in order of trials. It could be that trial 1 and trial 4 are the best way to find C rather than trial 1 and rather than trial 3 and trial 4. So it isn't just that it has to go this trial and the next one. You just choose to where only one concentration changes, the one you're interested in, and the others stay the same. That's what you're looking for. So if when you go down, multiple trials are changing, that's not going to help you out. Like if we compare trial 1 and 4 in this data set, everything changes, so that's not going to help me as much for finding what I need to do. So let's look at another example where I've got to determine a general rate law, but the numbers aren't nice and neat. See, here I have concentrations like 1 molar, 0.876 molar, and 0.42 molar, and the rate is 0.00220, 0.00169, 0.00039. Those numbers I can't neatly say, oh, that goes down by half, that doubles. If you have a case like this where you can't tell by inspection, you're going to have to solve it using math. So what we'll do is we're going to compare 2 of the rates to each other, and by dividing one by the other, we're going to be able to solve for the exponent that would appear in our rate law. Remember that the general rate law takes the form rate equals K, and in this case, A to the X power. You could also put an N, I believe your textbook does, lab did X. It doesn't matter what you do. Just make sure your variable's clear, so don't use like an O because it looks like a 0 or an I because it looks like a 1. But other than that, we're good. And what? So, now we have this. That's my general rate law. So what I need to do now is figure out how to find X. So we're given concentrations and rates, and if I divide 2 of these by each other, K stays constant, so it'll end up canceling out. So what I'm going to do is I'm going to compare runs 1 and 2. You can choose any set of runs you want. So I'm going to have rate 1 over rate 2 is equal to K, A, and this is going to be A at 1 to the X. So by A1, I mean this number here. I'm just leaving it in variable form for right now, so you can see what I'm doing. Divided by K, A to the X, but this time it's A at 2. So this is 2, this is 1. So now I need to figure out what can go away. So my K's cancel, and then I'm going to want to group the X's together because we only want one X, because right now X is in 2 places. So rate 1 over rate 2 is going to be equal to the concentration of A at 1 divided by the concentration of A at 2, all to the X power. I'm then going to take the log of both sides, And I'll note, you could go ahead and put your numbers in now if you'd like. I want you to see what the algebra looks like, especially for when you're trying to solve for something other than x, something like a or rate, where you may have to do more moving around. So I want to make sure you see how that works. So I'm going to leave it in variable form. But it's okay if you go ahead and plug in numbers. It will make your problem a little faster to do in this case. So here, we have the log of all of this to the x power. Because I have a logarithm, I can move my x to the front of it. So now we have log rate 1 over rate 2 is equal to x log concentration of A at 1 over concentration of A at 2. So whenever you don't... Why did it do that? I wish it would quit clicking away. Okay. Sorry about that. So now we've got our equation of log rate 1 over rate 2 equals x log A1 over A2. So now I'm going to go ahead and plug my numbers in. That way I can make it easier to solve. So when I do that, I'm going to get that we have log of 0.00220 molar per second. We're going to divide this by 0.00169 molar per second. And you'll notice the molar per seconds are going to cancel. And it's equal to x log 1.00 molar divided by 0.8. That should be a decimal. That's a real big decimal, but you'll see it now. 0.876 molar. Again, the concentrations cancel. I point this out not because because obviously the units all cancel, but that you need to pay attention to units because we've seen some problems where things don't just cancel, like when we do the Arrhenius problems next, where you end up with things like having to convert joules to kilojoules. So pay attention to your units. So now I'm going to do the math for these, and I'm going to get 0.1145 is equal to x times 0.05750. I'm then going to solve for x. I get x is equal to 1.99. That means we're going to be second order. Remember, we're going to round it to a close by integer, and that is basically 2. And so we get that rate is equal to k times a squared. And I'm fine with us leaving it for k here. I'm going to explicitly tell you to solve for k if you need to. So if you've been told to, though, you could plug in 1 molar for a and 0.00220 for rate, and then you could rearrange it and solve k, which means you would actually get, in this case, that k was equal to 0.00220. But you weren't asked for in this problem, so you don't have to do that. So I will make sure it will be very explicit. It will say solve for k, if that's something you need to do in your problem, just because I don't want you to spend a lot of time doing that most of the times. You'll probably do it once just to show me you know how to. So that's for our rate order questions. So now let's look at an Arrhenius-related question. So we have a reaction with a rate constant of 1.24 times 10 to the minus 3 inverse seconds at 25 degrees Celsius. We know it also has a rate constant of 0.0213 at 65 degrees Celsius. So this reaction, we're told 2 rate constants, 2 temperatures. We're then asked for what is the value of this rate constant at 45 degrees Celsius. So if we look at our Arrhenius equation, what we know is that with the first sets of information, we would be able to find the activation barrier, or the activation energy. That'll tell us how much energy that is. That'll give us EA. And if we have EA, then we can use the Arrhenius, the 2-point version of the Arrhenius a second time to be able to solve for what the rate must be at 45 degrees by choosing one of the other rate and times. So let's start by solving for EA. Note that you can use lots of forms of the Arrhenius equation. I am currently going to use the one that is on your equation sheet, but it is fine if you use a different one. Just make sure you're consistent in what you're doing, because the big change between different versions, like if you Google this, you'll see different ones. They'll have negatives in different places. These will be inverted. It's because there are lots of places where sign changes. You can change 2 signs at the same time, and that makes them look similar. It's important that what you do is mathematically correct, though. So make sure you're using a version of the Arrhenius equation that is consistent and you had just 1 extra negative somewhere, that it was because you did some mathematical operation. If you're worried about it, just use this version. That'll make your life easy. So what I'm going to start for this one is I'm actually just going to plug all the numbers in at the very beginning. So here, we're going to have ln, and I'm going to choose to make 1.24 times 10 to the minus 3 my k1. So I'm going to have 1.24 times 10 to the minus 3 inverse seconds. I'm going to divide this by 0.0213 inverse seconds. We're going to set this equal to EA, because we don't know our activation energy. We're going to divide it by 8.314 joules per mole Kelvin. Note, if you solve this problem by putting this in kilojoules at the start, that is A-okay. You could do it that way. We then have our temperatures. Our T2 is 65 degrees Celsius, which will give us 338 Kelvin when we convert it. And then we have to convert our 25, and that's going to give us 298 Kelvin. We're then going to put these numbers in our calculator, and I'm going to get negative 2.8436 equals EA over 8.314 joules per mole Kelvin times, let's see, negative 3.9712 times 10 to the negative fourth inverse Kelvin. So now I'm going to have to I'm going to take this negative 2.8436, I'm going to multiply it by 8.314, and then I'm going to divide it by negative 3.9712 times 10 to the minus fourth. I'm also going to see that my kelvins are going to cancel, and I'm going to get that my activation energy is equal to 59,500 joules per mole is EA. So that is step one of this problem. I've got 59,500 joules per mole. Now I'm going to use this to solve for K at 45 degrees Celsius. So I'm going to clear out all the stuff on the slide. And now we're going to do the equation a second time. So this time, I'm still plugging it into ln. I'm going to rewrite this part. So we're using the same equation, but now we're changing what we use for our K1 is what I'm going to do. You could also change K2. I don't care. That should be a T. That's T2. So whichever one you want to change is fine. So I'm going to make it so that K1 is my 45 degrees Celsius. So I'm going to say ln K1 over 0.0213 inverse seconds. So you just have to use one of the two rates from before. It doesn't matter which one. You could also use the 25 degrees Celsius one. I just picked the 55 degrees Celsius so I could leave it as K2. It doesn't matter. I'm then going to plug in my EA this time, which is 59,500 joules per mole. And then we're going to divide it by 8.314 joules per mole Kelvin. And then I've got to plug my temperatures in. So we still have 1 over 338 Kelvin for our T2. And then we have minus 1 over 318 Kelvin for our T1. Then I'm going to plug in some numbers. And over here on the right side, I'm going to get, and everything cancels, so I won't have a unit. I'm going to get negative 1.3317. And then on this side, I'm going to have the logarithm of K1 over 0.0213 inverse seconds. What I'm going to do now is I'm going to raise both of these to the e power. That way I can get rid of these logarithms to cancel. So I now have K1 over 0.0213 inverse seconds is equal to, let's see, e to that power is 0.26404. And then I'm going to solve for K1 by multiplying by this 0.0213 inverse seconds. And I'm going to get that my K1 is equal to 5.62 times 10 to the minus 3 inverse seconds. And so that is how I could use my Arrhenius 2-point formula to solve for a third rate constant when I was given two others. Note that I could make this problem smaller by doing something like giving you the activation energy and just asking you to solve for K1, K2, or T1 or T2. Or I could just ask for the activation energy. This example, though, is to show you what a longer problem could look like. This would be like a second to last problem on my exam, where I want it to be something you've seen before, but is challenging and is more steps than maybe you're doing a lot of your other problems. If the problem were written exactly as is, I would assume this is the longest or second longest problem on my exam. This would definitely not be a multiple choice, and it wouldn't be one of the shorter free responses, so it would have to be assumed to be a long part of your exam. As you noticed, I had to take a number of steps, and it may take a moment to recognize, oh, I need to first solve for activation energy, then I need to solve for rate. So I realized this would take a while, and we'll take that into account. So let's look at one more question. So this is a graphing type question. So we want to draw a reaction diagram for a reaction with the following qualities. The reaction is endothermic, the reaction has two elementary steps, and the second step is slower than the first step. So I'm going to do this. That's not even close to straight. I promise not to judge you on straightness, but I'm going to try one more time to see if I can get that to be actually straight. Let's see. Kind of. This pad is hard to draw on. Okay, and then this part. So what we have here, remember, this is energy. And I'm not worried about you labeling the x-axis necessarily, but if you remember to, it is reaction progress. So it's where we are in relation to reactants and products when we're going across a reaction for a particular set of molecules. So you've got to start here, and we're told first that it's a two-step process. That means when we draw our activation energy humps, we're going to have two of them. The second step is also slower than the first step, which is a way of me telling you that you're going to have a smaller hump first and then a larger hump because it's going to take more energy to get over the second step. Keep in mind, rather than giving it to you in words, I could have given you the amount of energy for each step. I could have drawn the steps and you would have to do that. You would have to figure out, oh, this one is smaller than this one, so it should be larger or smaller. So I'm going to go up like this. I'm going to get to my first activation barrier. It comes down some, but not as low as the original because it's intermediate. And then I'm going to make my second barrier, and it's going to go up more. Now, to figure out where to end it at, I know it is endothermic. Endothermic means that this should end above this. So when I draw this, I should have it set up so that delta H is positive because this is an endothermic reaction. Make sure that it is clear on your diagram whether delta H is positive or negative. If you want to, you can make sure it's a little exaggerated. Just make sure that the products aren't at a higher energy than one of your activation energy steps. And I suggest actually drawing a line like this where I've made it clear, hey, the reactants are supposed to be below the products. That way I can say delta H is positive, whereas if it was exothermic, I would have drawn this line lower down here where it would have been negative. So the main things to look at when doing this are that how your reactants and products compare to each other, how many humps you have in your activation energy area, and which ones are taller than which other ones to be able to figure this out.